Rows and columns. Hello, everyone. Now that we have established that a matrix is essentially a way to organize data into a rectangular array, it is essential that we move forward and understand exactly how this array is structured. The structure of any matrix is defined by two primary dimensions, the rows and the columns. It is absolutely critical that you clearly understand the difference between these two, as this distinction is fundamental to every operation we will perform in linear algebra as we progress through this course. Understanding rows. Now that we have established that a matrix is a rectangular array of data, let us take a closer look at its first primary dimension, the rows. First, by definition, a row is a horizontal arrangement of elements within a matrix. To help you visualize this, think about how you read a sentence in a book. You start from the left side of the page and move your eyes across to the right. Whenever you read a matrix in the same manner, from left to right, you are reading a row. To be very precise, the direction of a row is always horizontal. If you find this concept a bit abstract, consider a real-world analogy. Think of the rows of seats in a cinema or the way students are seated in a classroom. Each horizontal line of seats constitutes one single row. This is exactly how we identify rows within a mathematical matrix. Once you are comfortable with this horizontal structure, we will move on to the next slide to discuss the vertical dimension, which we call columns. Understanding columns. Now that we have a clear understanding of rows, let us move on to the second primary dimension of a matrix, the columns. A column is defined as a vertical arrangement of elements within a matrix. While we previously discussed reading rows from left to right, reading a column is different. If you look at a matrix from top to bottom, you are looking at a column. To put it simply, the direction of a column is always vertical. If you find it difficult to distinguish between the two, I suggest using this visual analogy. Think of the architectural columns or pillars that support a building. Just as those pillars stand upright and extend from the ground upwards, the columns in a matrix stand vertically. Now that we have defined both rows and columns, let us move forward and see how these concepts are applied in a real-world scenario involving inventory management. Real-world example, inventory management. Now that we have a theoretical understanding of what rows and columns are, let us put these concepts into practice with a real-world scenario to see how they function in a practical context. Imagine a small stationery shop that needs to keep track of its inventory. Specifically, the shop owner is monitoring the stock of two different items, notebooks and pens, which are distributed across 3 separate shelves. To begin, let us look at how this data is typically organized in a standard table. In the first column, we have our labels for the shelves: Shelf 1, Shelf 2, and Shelf 3. As we read across the rows, we can see the specific quantities for each shelf. For Shelf 1, there are 15 notebooks and 50 pens. For Shelf 2, there are 20 notebooks and 40 pens. And for Shelf 3, there are 10 notebooks and 60 pens. At this stage, the information is easy to interpret because of the headings. However, in the next slide, we will learn how to strip away these labels to represent this exact same data as a formal mathematical matrix. Converting the table into a matrix. Now that we have organized our inventory data into a table, let's transition this into a mathematical format. In linear algebra, a matrix is essentially a table stripped of its descriptive labels. By removing the headings such as shelf, notebooks, and pens, we can represent this data purely as a numerical array, which we will call matrix S. Looking at the screen, matrix S is shown as a rectangular array of numbers enclosed in large brackets. The first row contains the values 15 and 50. Directly below that, the second row contains 20 and 40. Finally, the third row contains 10 and 60. By presenting the data this way, we have a clean mathematical structure that allows us to perform calculations more efficiently. Now that we have successfully converted our table into matrix S, let's move forward and identify exactly how the rows and columns are structured within this specific matrix. Identifying the rows. Now, let us focus on matrix S, which we just derived from our stationary shop inventory. In this matrix, the rows represent the individual shelves. As we discussed earlier, remember that rows run horizontally from left to right. If we look at the first row, row 1, we see the elements 15 and 50. These values correspond to the stock on the first shelf. Moving down to the second row, row 2, we find the elements 20 and 40. And finally, the third row, row 3, consists of the elements 10 and 60. By counting these horizontal lines, we can conclude that there are a total of 3 rows in matrix S. Now that we have clearly identified the rows, let us move forward and examine the columns. Identifying the columns. Now, let us move from the horizontal view to the vertical view. In matrix S, the columns represent the different types of items we are tracking in our stationary shop. If you look at the first column, which we call column 1, you will see the elements 15, 20, and 10 arranged vertically. These values correspond to the number of notebooks across the 3 shelves. Next, looking at the second column, or column 2, we find the elements 50, 40, and 60. These values represent the stock of pens. Therefore, by counting these vertical arrangements, we can conclude that there are a total of 2 columns in matrix S. Common mistakes. Now that we have seen how to identify rows and columns using our stationary shop example, let us address some common pitfalls. It is very common for beginners to confuse rows and columns, so I want you to keep a few key points in mind to avoid these mistakes. First, let us talk about the confusion between horizontal and vertical directions. It is easy to swap these two, but a great way to remember the difference is to think of the word horizon. Just as the horizon is a flat line across the earth, rows are always horizontal. On the other hand, think of architectural columns or pillars that hold up a building. These are always vertical. So always remember, rows are horizontal and columns are vertical. Second, let us discuss the order in which we count and describe a matrix. This is a fundamental rule you must memorize. We always state the number of rows first, followed by the number of columns. For instance, if you have a matrix like the one we just analyzed, which had 3 rows and 2 columns, we call it a 3 by 2 matrix. It would be incorrect to call it a 2 by 3 matrix, as that would describe a completely different structure. Keeping these 2 rules in mind will ensure you do not make simple errors as we move toward our final summary in the next slide. Key takeaways. To conclude our lesson on this topic, let us review the key takeaways to ensure everything is clear. First, remember that rows are the horizontal lines of elements within a matrix. As we discussed earlier, you can think of these as the horizon or the rows of seats in a cinema. Similarly, columns are the vertical lines of elements. Just keep in mind the analogy of the architectural pillars that stand upright to support a building. The total number of these rows and columns is what defines the physical layout and the overall size of the matrix. This is why, as we noted in the previous slide, the order of counting is so important, always identifying the rows first and the columns second. Finally, in any matrix, which we can refer to as matrix A, the elements are organized such that they belong to a specific row and a specific column simultaneously. This means every single value has a unique address based on its vertical and horizontal position, a concept that will be very important as we move forward into more complex matrix operations.